What the edge of the universe really means, it's not a wall, it's not emptiness. It's something far more disturbing. When you think about the edge of the universe, you probably imagine a cosmic wall, a physical barrier where everything ends. Maybe you visualize space simply stopping, like falling off the edge of a cliff into absolute nothingness. But the truth is infinitely stranger. The horizon that moves by itself, the edge of the universe, is not a physical place. It's a cosmological horizon, an invisible boundary created by the very fabric of spacetime itself. Imagine being in the middle of an infinite ocean, where the horizon is always the same distance from you, no matter where you sail. The difference? This cosmic horizon shows us something truly terrifying. When we look at it, we see the universe still on fire. Hear us, what will blow your mind. The edge of the observable universe is currently about 46.5 billion light years away, even though the universe is only 13.8 billion years old. How is that possible? Two edges to destinies. There are actually two completely different edges in the universe, and they do opposite things. The particle horizon, what we can see. This is the boundary of the observable universe, the maximum distance from which light could have traveled to us since the Big Bang. Think of it as an invisible sphere of 46.5 billion light years around us. But here's the disturbing part. When we look at this extreme edge, we literally see the incandescent plasma from the first 380,000 years of the universe. A cosmos that's still burning. It's not darkness. It's not emptiness. It's cosmic fire frozen in time. The cosmic event horizon, our imprisoned future. This is a completely different boundary, currently about 16 billion light years away, and it marks the limit of everything we will ever be able to see in the future. Any galaxy beyond that line, its light will never reach us. Never. Not in trillions of years. The unnamed phenomenon, the zone of eternal freezing, and now we arrive at the part that scientists are still trying to name. As the expansion of the universe accelerates due to dark energy, something bizarre is happening. Light from distant galaxies is literally being dragged away from us, faster than it can travel in our direction. Imagine shouting to someone, but the ground between you is expanding so fast that the sound never arrives. Now imagine that happening with light itself, the fastest thing in the universe. The contradiction that breaks physics. Here is where everything becomes truly disturbing. Galaxies beyond a certain distance are moving away from us faster than the speed of light. You might be thinking, but wait, nothing can travel faster than light. And you're right. The difference? It's not the galaxy that's moving. It's the space itself between us and it that's expanding. It's as if someone is stretching the fabric of reality. The galaxies are stationary in their positions, but space grows between us like an inflating balloon. The frozen destiny. As the expansion of the universe accelerates, all objects outside our local supercluster will eventually appear to freeze in time, emitting progressively redder and fainter light. Imagine watching a distant galaxy. Now imagine observing it for billions of years. It doesn't disappear. It freezes. The movements within it become slower and slower, until it becomes an eternal photograph, glowing with light so red and faint that it eventually becomes invisible. It's not death. It's not annihilation. It's something worse, eternal existence trapped in the last observable moment, the unnameable mystery. And then there's the transition zone, the region where the particle horizon meets the event horizon. In this boundary, the redshift due to cosmic expansion becomes infinite, and no information can be transmitted through it. Scientists call it various things: cosmological horizon, observability limit, causal boundary. But none of these names capture what it really is, a point where the very laws of physics begin to behave in ways we don't fully understand. Recent research suggests that near event horizons, dark energy behaves strangely, as if space simply ignores the forces driving the universe's expansion. It's as if reality has exceptions to its own rules. The final truth. So what is the edge of the universe? It's not where space ends. It's not a wall you can touch. It's not absolute nothingness. It's an information horizon, a fundamental limit imposed by the speed of light, the age of the universe, and the accelerating expansion of space. It's the point where causality itself breaks down, where past and future separate eternally. It's the place where galaxies freeze in their last observable breath, where light is stretched until it disappears, where time for other regions of the cosmos becomes forever inaccessible. And with every passing second, this edge is closing in around us. The cosmic event horizon is shrinking, causing galaxies, black holes, and photons to cross this boundary, never to be observed again. The universe isn't just expanding, it's isolating us, trapping our observable bubble in a cocoon of ever-shrinking cosmic loneliness. And that is the edge of the universe, not an end, but a gradual and irreversible forgetting of everything that exists beyond our increasingly lonely island of light in the infinite cosmos. Why this region defies all the laws of physics we know from Einstein to quantum mechanics. Everything breaks down at the edge for over a century. Einstein's theory of general relativity has been our map of the cosmos. It predicted black holes before we saw them. It revealed gravitational waves before we detected them. It showed us how massive objects bend light and warp the fabric of space itself. But at the cosmic horizon, something goes terribly wrong. Einstein's equations begin to stutter. Quantum mechanics stops making sense, and the very foundations of physics start to crumble in ways that leave the greatest minds in science searching for answers. Einstein's cosmic glitch in 2024. Researchers at the University of Waterloo discovered something shocking. When we try to understand gravity on cosmic scales, at the scale of galaxy clusters and beyond, we encounter apparent inconsistencies with the predictions of general relativity. It's almost as if gravity itself stops perfectly matching Einstein's theory. Gravity becomes around 1% weaker when dealing with distances in the billions of light years. 1% might not sound like much, but in physics, 1% is the difference between a theory that works and a theory that's fundamentally incomplete. Think about it. Einstein's equations have predicted the behavior of light around black holes with stunning precision. They've guided spacecraft across the solar system with millimeter accuracy. They've never failed us in over 100 years of testing. Until we look at the cosmic horizon, the superhorizon, where relativity loses its grip, the problem emerges. At what scientists call the superhorizon, the maximum distance light has traveled since the beginning of the universe. Beyond this point, Einstein's carefully constructed framework starts behaving in ways he never anticipated. Scientists aren't saying Einstein was wrong. They're saying his theory is incomplete. Like Newton's laws of motion worked perfectly fine until Einstein came along and showed they were just a special case of something deeper. Einstein's relativity may itself be just a special case of something we haven't discovered yet. Quantum mechanics hits an impossible wall. But if Einstein's physics breaks down at the cosmic horizon, quantum mechanics absolutely shatters. Here's the problem. Quantum mechanics is built on a fundamental principle called the Heisenberg uncertainty principle. You can't know both the exact position and momentum of a particle simultaneously. The more precisely you measure one, the less you know about the other. This principle has been carved in stone since the 1920s. It's one of the unbreakable laws of nature. Except at the cosmic horizon, it breaks. The cosmological particle horizon is the maximum measurable length in the universe. The existence of such a maximum observable length scale implies a modification of the quantum uncertainty principle. The global properties of the universe produce a signature on the behavior of local quantum systems. In other words, the sheer existence of a cosmic horizon forces us to rewrite one of the most fundamental equations in all of quantum physics. The standard uncertainty principle has to be modified to include a new term, a maximum possible length. Beyond this length, quantum mechanics as we know it simply doesn't apply. The equations literally stop working. The entanglement paradox, one of the strangest predictions of quantum mechanics, is entanglement. Two particles can be connected in such a way that measuring one instantly affects the other, regardless of the distance between them. Einstein famously called this spooky action at a distance and refused to believe it was real. Turns out, Einstein was wrong about that one. Entanglement is real, and it's been experimentally verified thousands of times. But here's where things get weird at the cosmic horizon. If you have two entangled particles, and one of them crosses beyond the cosmic event horizon, quantum mechanics says they should still be connected. But general relativity says that's impossible, because no information can cross the horizon, not even quantum information. So which is it? Quantum mechanics cannot be used to communicate beyond event horizons. Entanglement is useless without a classical channel of information to compare notes. If one of your particles vanishes behind an event horizon, such a channel is unavailable. From your point of view, the particle will never actually cross the horizon, but gets frozen in time and becomes unobservable due to redshift. The particle is both beyond the horizon and frozen before it, depending on which theory you use to look at it. Quantum mechanics and relativity give contradictory answers about the same physical reality. The temperature paradox here is another mind-bending problem. Stephen Hawking showed in 1974 that black holes have a temperature. They emit thermal radiation because of quantum effects near the event horizon. If black hole event horizons have a temperature, then cosmic event horizons should too. Our universe should be bathed in a faint thermal glow coming from the edge of space itself. But we don't see this radiation. Or maybe we do, and we just can't distinguish it from the cosmic microwave background. Or maybe it is there, but quantum mechanics works differently at cosmic scales than it does at black hole scales. Nobody knows. The similarities between black holes and our universe don't end there. Both manifest event horizons, points of no return beyond which nothing can escape. But there is a critical difference. Almost all attempts to understand the cosmic horizon require physicists to artificially extricate themselves from the accelerating universe and imagine viewing it from the outside. This is a crucial simplifying assumption. It works for black holes because we can place an observer far away, but there seems to be no escaping our cosmological horizon. It surrounds us. It moves if we move, making the cosmic horizon problem much more difficult than the black hole problem. The horizon problem, why the universe shouldn't be uniform. Then there is what cosmologists call the horizon problem, one of the most unresolved issues in the Big Bang model. When we look at the cosmic microwave background radiation, the afterglow of the Big Bang, we see that it's almost perfectly uniform. The temperature is the same in all directions, to within 1 part in 100,000. But here's the problem. According to relativity, different regions of the sky that we observe in the cosmic microwave background were never in causal contact with each other. They were beyond each other's horizons. Light from one region could never have reached the other. So how did they all end up at exactly the same temperature? It is like finding that your soup is perfectly stirred even though you never actually stirred it, and the molecules in different parts of the bowl have never interacted with each other. Parts of the cosmic microwave background that are separated by about 1.7 degrees across the sky should be out of causal contact with each other. That the entire cosmic microwave background is in thermal equilibrium and approximates a black body so well is not explained by the standard explanations about the way the expansion of the universe proceeds. Where determinism dies, perhaps the most disturbing breakdown occurs at what's called the Cauchy horizon. Inside certain types of black holes, there's a boundary where the laws of cause and effect themselves break down. The Cauchy horizon is where the region determined by initial conditions ends. Strong cosmic censorship asserts that this horizon converts into a final singularity, where solutions cannot be extended beyond. But recent findings suggest that classically, this isn't always the case. What does this mean in plain language? It means there are regions of space-time where you could know everything about the past, have perfect information about every particle and field and force, and you still couldn't predict what happens next. Not because the equations are too hard to solve, but because the equations themselves stop making sense. Determinism, one of the most basic assumptions in all of physics, simply ceases to exist. Quantum theory comes to the rescue of strong cosmic censorship. When quantum effects are included, the stress tensor becomes infinite at the Cauchy horizon, rendering the Einstein equations ill-defined. Quantum fields oscillate infinitely rapidly as you approach this boundary, creating a blue-shift effect so extreme that it tears apart the fabric of spacetime itself. The breakdown cascade what we're seeing isn't just one theory failing, it's a cascade of breakdowns. Einstein's relativity stops matching observations at cosmic scales. Quantum mechanics requires modification to even describe a universe with horizons. Entanglement paradoxes create contradictions between the theories. Temperature predictions don't match reality. Causality fails. Determinism ends. It is as if the universe itself is telling us, your physics works beautifully for everything you can touch, measure, and experiment with. But out here, at the edges of reality, where space and time begin to blur into something else entirely, your equations are just approximations, shadows of something deeper that you haven't discovered yet, the search for quantum gravity. This is why physicists are obsessed with finding a theory of quantum gravity, a theory that can unify Einstein's relativity with quantum mechanics, a theory that doesn't break down at horizons. String theory is one attempt, loop quantum gravity is another. Some physicists are exploring whether spacetime itself is not continuous, but made of discrete chunks, at the smallest scales. Others think the answer lies in something called holography, where the three-dimensional universe we perceive is actually encoded on a two-dimensional surface, like a cosmic event horizon. Recent breakthroughs from black hole physics, which required understanding regimes where quantum mechanics and gravity are equally important, could help extract answers in quantum cosmology. Many luminaries in physics are bursting with ideas and ready to get to work on the crossover between black hole event horizons and cosmological horizons. What it all means, the cosmic horizon isn't just a boundary in space. It's a boundary of knowledge itself, a limit beyond which our most fundamental theories stop functioning. Known physics breaks down beyond the event horizon. As no information can escape, we can have no experience as to what lies inside. We build our understanding of the universe onto pillars, Einstein's relativity, and quantum mechanics. Both are among the most successful scientific theories ever created. Both have been tested to extraordinary precision. And at the edge of the universe, both fail. This isn't a crisis, it's an opportunity. Because every time physics has encountered a fundamental limit like this, every time our equations have broken down and stopped making sense, we've discovered something revolutionary on the other side. Newton's physics broke down at high speeds, and we discovered relativity. Classical physics broke down at atomic scales, and we discovered quantum mechanics. Now both relativity and quantum mechanics are breaking down at the cosmic horizon. What lies beyond this breakdown might be the greatest discovery in the history of science. A new physics, a deeper understanding of reality, a glimpse into the true nature of existence that makes everything we currently know look like child's play. A discovery so recent and strange it is making the world's greatest scientists rethink everything about the origin and destiny of the cosmos. In March 2025, something happened that sent shockwaves through the scientific world. Not an explosion, not a cosmic catastrophe, but something potentially more profound. Over 900 researchers from 70 institutions around the globe had been quietly mapping the universe for 3 years using the dark energy spectroscopic instrument known as DESI. They'd measured nearly 15 million galaxies and quasars, creating the largest three-dimensional map of the cosmos ever made. What they found doesn't have a proper name yet, because we've never seen anything like it before. The force that's fading away for 27 years, since 1998. Scientists have believed in a fundamental constant of the universe, dark energy, the mysterious force that makes up 70% of everything that exists. The force that's been pushing the universe apart, making its expansion accelerate faster and faster. We called it a cosmological constant because we thought it was unchanging, eternal, fixed since the beginning of time. We were wrong. Dark energy is weakening. It's becoming less pushy over time. The force that's been driving the universe's expansion for billions of years is gradually fading away, and nobody knows what happens next. When the data speaks, scientists listen. The first hints appeared in April 2024. DESI's initial year of data showed something odd, a subtle pattern that didn't quite match our models. The scientists were cautious. Statistical anomalies happen. You need more evidence before you upend everything we know about the universe. So they kept observing, kept measuring, doubled their dataset. The anomaly didn't go away. It got stronger. By March 2025, when DESI released its 3-year analysis, the evidence had become impossible to ignore. When they combined their measurements with data from exploding stars, the cosmic microwave background, and gravitational lensing, everything pointed in the same direction. Dark energy is evolving, changing, weakening with time. The signal reached what's called 4.2 sigma in some analyses. That means there's less than a 1 in 50,000 chance this is just a statistical fluke, not quite the gold standard of 5 sigma that physics requires for a discovery, but close. Uncomfortably close. Professor Mustafa Ishaq Baushaki from the University of Texas at Dallas, who led the analysis, put it bluntly, if these results hold up, we need to stop, sit down, and rethink our model of the universe. We need to revise our understanding of basic physics, our understanding of the Big Bang itself, and our understanding of the long-range forecast for the universe. The universe that shouldn't exist. Here's what makes this discovery so disturbing. Every major cosmological observation we've made in the past century has been explained by what we call the lambda CDM model, the standard model of cosmology. Lambda represents dark energy as a constant. CDM represents cold dark matter. This model has been tested thousands of times. It's survived every challenge. It's explained the cosmic microwave background, the formation of galaxies, the distribution of matter across billions of light years of space. It's the best scientific theory about the universe we've ever had. And now it's breaking. When you take DESI's data alone, it still fits the standard model. But when you combine it with other independent measurements from different telescopes, different methods, different teams of scientists who weren't even trying to challenge the model, the pieces stop fitting together. The universe we observe is not the universe our equations predict. Will Percival, co-spokesperson for DESI and professor at the University of Waterloo, explained it this way: we're guided by a Cam's razor, and the simplest explanation for what we see is shifting. It is looking more and more like we may need to modify our standard model of cosmology to make these different datasets make sense together. And evolving dark energy seems promising. The detective novel written by the universe scientists are calling this a detective story. We've found clues that don't match the case we thought we'd solved, and now we're scrambling to figure out what we missed. The evidence comes from measuring something called baryon acoustic oscillations, sound waves from the early universe that left ripples frozen in the distribution of galaxies. These ripples act like a cosmic ruler, allowing scientists to measure how the universe was expanding at different points in its history. DESI mapped 6 million galaxies spanning 12 billion years of cosmic history. They could see these frozen sound waves at different distances, at different times, and what they saw was dark energy's strength changing, getting weaker as the universe aged. At the beginning of the universe, dark energy was very strong. Over billions of years, it weakened, and if the trend continues, it will keep weakening. Michael Levi, director of DESI, captured the excitement perfectly. This is why I love doing physics. It's a detective novel that you get to read and discover, and it was written by the universe. 3 possible futures, none of them certain if dark energy continues to weaken. 3 potential futures open up before us. Future 1. The big freeze continues. Dark energy keeps fading, but never disappears completely. The universe keeps expanding, but the acceleration slows down. Eventually, expansion happens at a constant rate. Matter spreads out across space. Stars burn out. Galaxies drift apart into eternal darkness. The heat death of the universe, just taking longer than we thought. Future 2. The big crunch. Dark energy doesn't just weaken, it reverses. What was pushing the universe apart starts pulling it together. The expansion stops, then reverses. The universe begins to collapse back on itself. All of space, all of matter, all of energy, crushed back together in a cosmic apocalypse. Some estimates suggest this could happen in 11 billion years, with the final crunch 8 billion years after that. Future 3. Something we haven't imagined. Dark energy is telling us something fundamental about reality that we don't understand yet. Maybe it's not even energy. Maybe it's a sign that gravity works differently on cosmic scales. Maybe spacetime itself behaves in ways our equations don't capture. Maybe there are hidden dimensions, extra forces, phenomena we can't even conceive of yet. Professor Carlos Frank from Durham University said it plainly: if DESI's hints are right, our earlier understanding goes out the window, and essentially we have to start from scratch. The hypothesis that changes everything. Some scientists think the answer might involve particles called axions, still theoretical, still undetected, but potentially responsible for everything we're seeing. According to this new model, dark energy isn't just one thing. It's 2 things working in opposite directions. Axions pushing the universe apart, and the cosmological constant, which isn't constant at all, trying to pull everything back together. In the early universe, axions dominated. But as space expanded, they spread out, weakened. Eventually, the cosmological constant will take over. And when it does, the expansion stops. The universe begins contracting. The big crunch becomes inevitable. Black holes as cosmic engines, another theory gaining traction, suggests something even stranger. Black holes might be generating dark energy, not consuming it, generating it. Recent observations show that supermassive black holes in dead galaxies, galaxies that stopped forming stars billions of years ago, are still growing. They shouldn't be. They have no fuel, no nearby matter to consume, but they're expanding anyway. Some researchers believe black holes are coupled to the expansion of the universe itself. As space grows, black holes grow with it, and in the process, they might be creating the dark energy that drives the expansion in the first place. If this is true, black holes aren't just endpoints for matter. They're engines of expansion. The universe is powering its own growth through the very objects we thought were its darkest, most destructive forces. The universe without dark matter. And then there's the most radical proposal of all. What if dark energy and dark matter don't exist? In 2024, physicist Rajendra Gupta published a model that explains all our observations without requiring either mysterious component. Instead, he suggests that the forces of nature themselves are weakening as the universe expands. What we interpret as dark energy is actually just gravity and other fundamental forces, getting weaker over cosmic time scales. His model matches the data. It explains galaxy distributions. It fits the cosmic microwave background. It might even explain why the universe appears to be 26.7 billion years old, instead of 13.8 billion. If he's right, we've been chasing phantoms. 70% of the universe that we thought was dark energy, 27% that we thought was dark matter, they might not exist at all. The crisis that isn't a crisis right now, cosmology, is at what scientists are calling a tipping point. The media is reporting it as a crisis. Headlines scream about the standard model falling apart, about physics in chaos, about scientists not knowing what's real anymore. But the scientists themselves, they're excited. Because every time physics has hit a wall like this, every time our best theories have stopped working, we've discovered something revolutionary on the other side. When Newton's physics broke down at high speeds, we discovered relativity and learned that time and space aren't separate things, but woven together in space-time. When classical physics broke down at atomic scales, we discovered quantum mechanics and learned that reality at its smallest level is probabilistic, not deterministic. Now our cosmology is breaking down at the largest scales imaginable. Both relativity and quantum mechanics are failing us at the cosmic horizon. What lies beyond this breakdown? The phenomenon that has no name. We don't have a name for what Desi has discovered because we don't fully understand it yet. Is it evolving dark energy? Is it decaying dark matter? Is it weakening fundamental forces? Is it black holes generating energy from the vacuum of space? Is it axions and negative cosmological constants? Is it a sign that spacetime itself has properties we've never imagined? We don't know. What we do know is this: the universe's expansion history, mapped across 11 billion years, doesn't match what our equations predict. Multiple independent measurements from different experiments all point to the same conclusion. Something is changing. Something fundamental about the cosmos is evolving in ways we never anticipated. Scientists have 5 years to figure it out. The Vera Rubin Observatory in Chile, home to the world's most powerful digital camera, began operations in 2025. Over the next 5 years, it will discover more than 20,000 new supernova host galaxies. DESI will continue mapping tens of millions more galaxies. By 2030, we'll have enough data to know for certain whether dark energy is truly evolving or if this is all a massive systematic error we haven't accounted for. What it means for us if dark energy is weakening, if the universe's fate is truly uncertain. What does that mean for humanity? In the immediate term, nothing. These changes happen over billions of years. The sun will die long before the universe does anything unexpected. But philosophically, existentially, it means we live in a universe far stranger and more dynamic than we ever imagined. A universe where even the most fundamental forces aren't permanent, where the rules can change, where the future is genuinely unknown. For decades, we thought we knew the universe's fate. Heat death, eternal expansion, slow decay into darkness. Now, the universe might collapse, or stabilize, or do something we haven't even conceived of. The nameless phenomenon at the edge of the universe is telling us something profound. The cosmos is still full of surprises. We haven't solved it. We haven't figured it out. We're not even close. And that's the most exciting discovery of all. Prepare to question everything you thought you knew about the universe for thousands of years. Humans believed time flowed like a river. Universal. Absolute. The same for everyone, everywhere. Isaac Newton built his laws of physics on this foundation. Time was the stage upon which the universe performed its cosmic ballet. Then Einstein shattered that illusion. Time, he showed us, is not a river. It's a dimension woven together with space into a single fabric called space-time. And this fabric bends, stretches, warps. Time itself becomes relative. But even Einstein couldn't have imagined what we're discovering at the cosmic horizon. Because there, time doesn't just slow down or speed up. It breaks. The teleological nature of reality here's something that will twist your mind into knots. Event horizons, whether around black holes or at the edge of the cosmos, are what physicists call teleological. That means they're determined by future causes, not past ones. To know whether an event horizon exists at a specific point in space, you would need to know the entire history of the universe all the way into the infinite future. You cannot determine the presence of an event horizon by looking at the past or present alone. It's defined by what hasn't happened yet. Think about that. The existence of a boundary in space today depends on events that won't occur for billions or trillions of years. Cause and effect, the bedrock of all science, runs backward. The paradox of the falling observer. Imagine you're falling toward a black hole's event horizon. From your perspective, nothing special happens as you cross it. You pass through the boundary in a finite amount of your proper time. You don't feel anything unusual. The horizon isn't a physical barrier. It's just a mathematical surface. But to someone watching you from far away, they never see you cross. You approach the horizon, but you never quite reach it. Your image becomes more and more redshifted, dimmer and dimmer, slower and slower, until you appear to freeze at the horizon, stuck there for eternity. So which is real? Do you cross the horizon or don't you? The disturbing answer is both. Depending on which coordinate system you choose, which reference frame you adopt, the universe gives different answers about objective physical reality. Time doesn't have a single, universal flow. It fractures into incompatible perspectives that are all equally valid. The cosmic time that isn't time in cosmology. There's something called comoving time. It's a universal time coordinate that records the time since the Big Bang. All observers who are at rest relative to the expansion of the universe share this time coordinate. This seems to suggest that time is absolute after all, that there's a universal clock ticking away since the beginning. But here's the catch. This universal time only works if you ignore gravity. The moment you account for general relativity, for the actual curvature of spacetime, comoving time becomes an approximation, a convenient fiction. Recent research suggests that to properly predict cosmological redshift, the time we observe in distant galaxies, we need to use something called conformal time instead of coordinate time. Conformal time accounts for cosmic time dilation. It means time literally runs differently at high redshifts than it does now. The distant universe doesn't just look different. Time there actually flows at a different rate. Space without time, time without space. At the cosmic event horizon, something even stranger happens. The redshift due to cosmic expansion becomes infinite. Objects freeze. Light stretches into invisibility, and the distinction between space and time begins to blur. Inside a black hole's event horizon, the roles of time and space actually swap. What was a spatial dimension becomes a temporal one. Moving toward the singularity becomes as inevitable as moving forward in time. You can't avoid it any more than you can avoid tomorrow. At the cosmic horizon, similar distortions occur. The coordinate systems we use to map spacetime simply stop working. They develop singularities, not physical singularities like the center of a black hole, but coordinate singularities, places where our mathematical descriptions break down even though nothing physically unusual is happening. It's like trying to use latitude and longitude to describe the North Pole. The coordinates become undefined, not because there's anything wrong with the North Pole, but because our mapping system fails. Except in this case, it's not just our maps that fail. It's our concept of time and space themselves, the holographic revelation. But the deepest challenge to our understanding of reality comes from something called the holographic principle. In the 1990s, physicists Gerard T. Hooft and Leonard Susskind proposed something that sounds like science fiction. They suggested that all the information contained in a volume of space can be encoded on the boundary of that region, like a hologram, which stores three-dimensional information on a two-dimensional surface. Susskind described it this way: the three-dimensional world of ordinary experience, the universe filled with galaxies, stars, planets, houses, boulders, and people, is a hologram, an image of reality coded on a distant two-dimensional surface. This isn't metaphor. This is mathematics. In 1997, Juan Maldacena, then only 29 years old, proved this principle works for certain types of universes. He showed that a five-dimensional universe with gravity is completely equivalent to a four-dimensional universe without gravity. All the physics happening in the higher dimensional space can be perfectly described by a theory living on its boundary. Two completely different descriptions, different numbers of dimensions, different laws of physics, but mathematically identical dual. Are we living in a projection? If the holographic principle applies to our universe, and many physicists believe it does, then everything you see, everything you touch, every thought you think, is encoded as information on a two-dimensional surface. That surface might be the cosmic horizon, the boundary of the observable universe, 46.5 billion light-years away. All the information about our three-dimensional reality could be painted on that distant two-dimensional screen. Or maybe not. Recent theories by physicists Brian Swingle and Mark van Romstunk suggest the holographic screen might exist in something called imaginary time, a mathematical dimension where time behaves like space. In their model, our universe is encoded on the ends of a plane existing in imaginary time. The two ends are connected by a wormhole, a tunnel through space-time, and this structure predicts something terrifying: the Big Crunch. Their mathematics suggests that our universe's expansion will eventually stop, then reverse. Space will begin contracting, pulling everything back together until the entire universe collapses into a black hole singularity. And all of this, all of reality as we know it, would be just a three-dimensional projection of information encoded on a two-dimensional surface we can't even see. Information as the fabric of reality. The holographic principle leads to an even more radical idea. Maybe matter and energy aren't fundamental. Maybe what's fundamental is information. In 2003, physicist Jacob Bekenstein wrote, "Scientists may regard the physical world as made of information, with energy and matter as incidentals. Every particle, every force, every interaction in the universe might be just the manifestation of pure information. Bits and bytes, like the code running on a cosmic computer. The position of an object, its velocity, its quantum state. These aren't properties of matter. They're information. And that information is what's real. The matter we perceive is just how that information expresses itself in three dimensions. This connects deeply to entropy, the physicist's measure of disorder. Shannon entropy in information theory has exactly the same mathematical form as thermodynamic entropy in physics. They're the same thing. When you throw a book into a black hole, you're not destroying matter. You're erasing information, and that information gets encoded on the black hole's event horizon. As tiny increases in its surface area, the universe isn't made of stuff. It's made of information about stuff. The breakdown of determinism inside certain black holes. There's something called a Cauchy horizon. It's a boundary where something unprecedented happens. Determinism ends. Below the Cauchy horizon, you could know everything about the past, every single detail, have perfect information, and you still couldn't predict what happens next. Not because the equations are too complex, not because you lack computing power, but because the equations themselves become undefined. The future literally separates from the past. Cause and effect break their connection. Recent quantum calculations show that near this horizon, quantum fields oscillate infinitely rapidly. The energy density becomes infinite. The fabric of spacetime itself gets torn apart. This isn't just theoretical. This is what the mathematics of general relativity and quantum mechanics predict. At certain boundaries in spacetime, reality loses its logical structure. Time dilation at infinity. Let's return to time dilation, but with a cosmic twist. As an object approaches the cosmic event horizon, we see its clock slow down. Just like with a black hole, light from the object becomes increasingly redshifted. Eventually, the object appears to freeze at the horizon, its last photons stretched into invisibility. But does time actually stop there? Or does it just appear to stop from our perspective? The answer matters because of what it means for the rest of the universe. Galaxies beyond our cosmic event horizon are crossing that boundary right now. From our perspective, they're slowing down, freezing, fading away. But from their perspective, nothing unusual is happening. Time flows normally. The universe continues evolving. So which is real? The universe where time stops at the horizon, or the universe where it continues beyond it? Both, neither. The question itself may be meaningless. Time might not have a universal answer. Reality might be fundamentally relative. The illusion of three dimensions, if the holographic principle is true, then the third dimension of space is an illusion. A very convincing illusion, but an illusion nonetheless. You, sitting there reading this, are not fundamentally a three-dimensional being. Your information encoded on a two-dimensional surface. The three-dimensional you is a projection, a hologram. Your thoughts, your memories, your consciousness, everything you experience as depth and volume and solidity, is actually information living in a lower dimensional reality. Physicist Matthew Hedrick puts it this way: the universe around us, which we are used to thinking of as being three-dimensional, is actually at a more fundamental level two-dimensional. And everything we see going on around us in three dimensions is actually happening in a two-dimensional space. The limits of knowledge, but here's what might be the most profound implication of all. If event horizons exist, if they truly prevent any information from crossing them, then there are fundamental limits to what we can know about the universe. Not practical limits, not technological limits, fundamental limits built into the structure of reality itself. No experiment, no measurement, no observation, no matter how advanced our technology becomes, can tell us what lies beyond our cosmic horizon. That information is forever inaccessible. The universe could be infinite, or it could end just beyond what we can see, or it could loop back on itself, or split into parallel realities, or do something we can't even imagine. We will never know, because the cosmic horizon doesn't just limit what we can see, it limits what can be known. Period. Questioning everything. So what does all this mean? It means time isn't what you think it is. It's not universal. It's not absolute. It depends on where you are, how fast you're moving, how close you are to massive objects, and which reference frame you choose. It means space might not have three dimensions. The depth you perceive might be a projection from a flatter reality. It means cause and effect aren't fundamental. There are regions of spacetime where the future isn't determined by the past. It means information might be more fundamental than matter and energy. Reality might be made of bits, not atoms. It means there are questions about the universe that cannot be answered, not because we're not smart enough or don't have the right tools, but because the answers lie beyond boundaries that cannot be crossed. It means the comfortable, intuitive world of solid objects moving through space and time is an approximation, a shadow, a hologram cast by a deeper reality we can barely glimpse. At the cosmic horizon, everything we thought we knew about time, space, and reality breaks down. And in that breakdown, we're catching our first glimpse of something far stranger and more profound than we ever imagined. The universe isn't just vast and old and complex. It's fundamentally different from what our everyday experience suggests. And we're only beginning to understand just how different it really is. Every second of this journey brings you closer to a truth that will shatter everything you thought you knew. You've traveled far. You've seen how the edge of the universe isn't a wall, but a horizon of frozen time. You've watched Einstein's equations crumble at cosmic scales. You've witnessed dark energy weakening, potentially reversing, threatening to collapse everything back into a singularity. You've learned that time isn't universal, that space might be an illusion, that reality itself could be a hologram projected from a two-dimensional surface we can never see. But now we arrive at the final piece, the revelation that connects everything, the possibility so profound that it transforms every question about the universe's beginning and end into something far stranger. What if there is no beginning? What if there is no end? What if the universe is an eternal loop? The Cosmic Ouroboros in 2010. Nobel Prize winner Roger Penrose proposed something that sounds like ancient mythology. Dressed in modern mathematics, he called it conformal cyclic cosmology. The universe doesn't end in a big crunch or a big freeze or a big rip. It transforms. The infinitely expanded, cold, dead end of one universe becomes the hot, dense Big Bang of the next. Not through collapse, not through bouncing, but through a mathematical trick so elegant it borders on poetry. At the end of our universe, trillions upon trillions of years from now, all the stars will have burned out. All the black holes will have evaporated through Hawking radiation. Matter will be so dispersed that the entire cosmos becomes smooth, empty, timeless. And in that smoothness, something extraordinary happens. Scale loses meaning. When infinity becomes zero, here's the mind-bending part. When the universe becomes perfectly smooth, when there's no matter left to serve as a reference point, there's no way to measure scale. An infinitely large empty space looks identical to an infinitely small point. Penrose realized you could mathematically connect the infinite future of one universe to the Big Bang singularity of the next through what is called a conformal transformation, a rescaling that preserves the shape of spacetime, but not its size. The whimper at the end of one cosmos becomes the bang at the beginning of another, and this process repeats forever, through an infinite sequence of universes that Penrose calls eons. Our Big Bang, it was the smooth, cold death of a previous universe. Our eventual heat death, it will be the explosive birth of the next, the evidence hiding in plain sight. But this isn't just mathematical speculation. Penrose predicted something testable. If his theory is correct, extremely energetic events from the previous eon should leave signatures in our cosmic microwave background. The afterglow of the Big Bang, the oldest light in our universe. Specifically, he predicted we should see two types of anomalies, Hawking points, bright spots left by the final evaporation of supermassive black holes from the previous universe, their last burst of Hawking radiation crossing the boundary between eons. Concentric circles, ripples created by black hole collisions in the previous cosmos, preserved across the transition like cosmic echoes. And in 2010, Penrose and physicist Veit Gerzadian announced they'd found them, circular patterns in the cosmic microwave background that shouldn't be there. According to standard cosmology, the scientific community erupted in debate. Some claimed the signals were just random noise. Others insisted they were real. The controversy continues, but recent analysis suggests the anomalous regions exist. Bright spots that match Penrose's predictions. Potential evidence that our universe remembers its previous life. The loop that bites its tail, here's where it gets even stranger. Penrose himself considered, but rejected a radical interpretation of his theory. What if the sequence of eons doesn't stretch infinitely forward and backward? What if there's only one eon? What if our universe's end connects directly to its own beginning? A cosmic loop, the ultimate Ouroboros, the serpent eating its tail on the grandest scale imaginable. Philosopher Baptiste Le Béhan calls this eon monism, the idea that there's only one universe, endlessly repeating itself. Everything that has happened will happen again. Everything that will happen has happened before. Eternal recurrence, not metaphorically, not philosophically, but as the actual structure of physical reality. You've lived this life before. If eon monism is correct, then this moment right now, you reading these words, has happened an infinite number of times before. Every choice you've made before. Every thought you've had before. Every person you've loved before. The universe reaches its end. And then, through conformal geometry, that end connects seamlessly to its beginning. And everything plays out exactly the same way. Forever. No beginning. No end. Just an eternal present playing on infinite repeat. How everything connects. Now watch how all the pieces fall into place. The edge of the universe isn't a boundary. It's a transformation point where one cycle gives way to the next. The breakdown of physics at cosmic horizons makes sense, because those horizons are where eons connect, where the rules have to reshape themselves for the transition. Dark energy weakening isn't just changing the universe's fate. It's preparing the cosmos for its transformation into the next cycle. The holographic principle works because information doesn't need to survive inside the eon. It's encoded on the boundary that connects one cycle to the next. Time and space breaking down at horizons happens because those are the seams in reality where one universe is stitched to another or to itself. The Big Crunch meets the eternal loop. Remember the recent discoveries about dark energy weakening? About the possibility of a big crunch in 11 billion years, with the universe collapsing back to a singularity after 33 billion years of total existence? What if that's not the end? What if the Big Crunch is just another form of conformal transition? The universe collapsing not into nothingness, but into the conditions for its own rebirth? Some holographic models suggest exactly this. The universe encoded on a surface in imaginary time, connected by a wormhole, cycling through expansion and contraction in an eternal rhythm. Birth, growth, death, rebirth. Over and over and over. The multiverse inside a single universe. Here's the final twist that will truly explode your mind. If eon monism is correct, if our universe is a loop repeating itself eternally, then every possible universe that could exist does exist. Not as parallel realities, but as the same reality played infinitely many times. Every quantum possibility, every branching path, every alternative version of history. They all happen. They've all happened. They're all happening now in some iteration of the eternal loop. The multiverse isn't out there somewhere beyond our horizon. It's here. It's now. It's every moment stretched across eternity. What it means you came here looking for answers about the edge of the universe. What you've found is far stranger. The edge isn't an ending. It's a transformation, a boundary where one version of reality becomes another. Time isn't linear. It's circular. Or maybe it's a single eternal moment that contains everything that ever was or ever will be. Space isn't three-dimensional. It's a hologram projected from information encoded on surfaces we can't directly observe. Matter and energy aren't fundamental. Information is. And that information survives the transition between eons, carrying the memory of previous universes into the next. The universe doesn't die. It transforms. It doesn't begin. It has always existed. It doesn't end. It cycles forever. The revelation everything you've learned in this journey connects to one profound truth. The universe is not a story with a beginning, middle, and end. It's a loop, a cycle, an eternal present containing all of time within itself. You are not living through a single moment in a linear timeline, stretching from the Big Bang to heat death. You are part of an eternal pattern that has repeated countless times and will repeat countless more. Every star that burns has burned before. Every galaxy that forms has formed before. Every consciousness that awakens has awakened before. We are not heading toward an unknown future. We are living through a cosmic pattern that has no beginning and no end, only eternal transformation. The edge of the universe is not where reality stops. It's where reality loops back on itself, where the infinite becomes the infinitesimal, where the end becomes the beginning. We don't live in a universe that will someday die. We live in a universe that will someday become itself again. Stay until the end. The final revelation will completely change your perspective on our existence in the cosmos. You've journeyed through the frozen horizons where galaxies hang suspended in eternal time. You've witnessed Einstein's equations crumble and quantum mechanics shatter at the edge of reality. You've learned that dark energy is weakening, that the universe might be an eternal loop, that time and space themselves might be illusions projected from a lower dimensional surface. But there's one final piece, one revelation that ties everything together and changes what it means to be you here, now, reading these words. The question that will haunt you forever. Why are you observing this particular universe at all? The privilege of existence. Think about the cosmic lottery you've won just by being here. The fundamental constants of physics, the strength of gravity, the mass of the electron, the charge of a proton. If any of these values were even slightly different, atoms couldn't form, stars couldn't burn, chemistry couldn't happen, life would be impossible. The probability of our universe having exactly the right constants to support life, astronomically small. 1 part in 10 to the power of 120. That's not a million, not a billion, not a trillion. It's a 1 followed by 120 zeros. A number so vast it exceeds the number of atoms in the observable universe. Yet here we are. The anthropic selection effect. Scientists call this the anthropic principle, but that name barely captures its profound implications. The universe can only be observed by observers, and observers can only exist in a universe precisely fine-tuned to create them. It's not that the universe was designed for us. It's that we can only find ourselves in a universe capable of producing us. But here's where it gets disturbing. If there's only one universe, this is an impossible coincidence. A cosmic accident so improbable it strains all rational explanation. Unless you are the universe observing itself, what if observation isn't just a passive act? What if the very existence of observers is what makes the universe real? The universe without observers is just a mathematical equation, a wave function describing infinite possibilities. Schrödinger's cat, alive and dead simultaneously. It's only when an observer looks that reality chooses. And you, reading this now, are that observer. The cosmic horizon, the edge where information stops flowing, the boundary where cause and effect break down. That's not just a physical limit. It's the boundary of your consciousness projecting itself into reality. The participatory universe physicist John Wheeler proposed something radical before he died. He called it the participatory universe. The universe doesn't exist out there independent of observation. The universe comes into being through observation. Past, present, and future aren't fixed. They're brought into existence by observers making measurements, collapsing wave functions, turning infinite possibility into singular actuality. You're not just observing the universe, you're creating it, moment by moment, with every observation you make. The delayed choice quantum eraser experiments prove this. Measurements made now can affect the path a photon took in the past. The present creates the past. Observation determines history. The cosmic coincidence now connect all the pieces. The edge of the universe is where observation stops. Beyond that boundary, no information can reach you. No measurement can be made. Reality literally doesn't exist there in any meaningful sense for you. The holographic principle says reality is information encoded on a surface, and that information only becomes real when observed. The eternal return, the cosmic loop. Maybe it's not just the universe repeating. Maybe it's consciousness itself, recurring infinitely, bringing the universe into existence again and again through eternal observation. Dark energy weakening, physics breaking down at horizons, time and space dissolving into something stranger. Maybe these aren't just physical phenomena. Maybe they're symptoms of consciousness reaching the limits of what it can observe into existence. The selection effect of your existence. Here's the revelation that changes everything. You can only observe a universe that produced you. That means every version of you that could possibly exist is observing a different cosmic configuration, a different set of physical constants, a different history, a different future. The multiverse isn't out there somewhere. It's here. Every possible observer experiencing every possible universe they could exist in. You're not one consciousness observing one universe. You're one perspective in an infinite sea of observer moments, each bringing their own version of reality into existence. When you look at the cosmic horizon, you're not seeing the edge of space. You're seeing the edge of what your consciousness can bring into existence. The isolation isn't physical. The cosmic event horizon is shrinking. Galaxies disappearing beyond our observational reach. The universe isolating us in an ever smaller bubble of causally connected space. But maybe this isn't happening to physical space. Maybe it's happening to observational space. As the universe ages, as entropy increases, as structure breaks down, the number of possible observation points decreases. The cosmic consciousness that brings reality into existence contracts, consolidates, simplifies. The heat death isn't the end of matter and energy. It's the end of the ability to observe. The end of consciousness differentiating itself into distinct perspectives. And when the last observation is made, when the final consciousness observes the final moment, that's when the infinite becomes the infinitesimal, when the end becomes the beginning, when the loop closes. You have always been here if consciousness is what brings the universe into existence through observation. And if the universe loops eternally, then you have always been here. Not your memories, not your body, but the fundamental act of observation that makes you you. The subjective experience of being something rather than nothing. That's eternal. That's the loop. That's what survives the transition between eons. Every time the universe cycles, consciousness emerges again, differentiates into billions of observer moments, each one bringing their own perspective of reality into existence. You've lived this before. You'll live it again, not as the same person, but as the same fundamental act of observation wearing a different form. The final truth, the edge of the universe isn't where reality stops. It's where your ability to create reality stops. Beyond that horizon, the universe doesn't exist in any meaningful sense. Not because there's nothing there, but because there's no observation to make it real. You are not in the universe. The universe is in you, a construction of consciousness interpreting quantum possibilities into classical certainty. The cosmic horizon shrinking, that's the observation space collapsing, the number of possible perspectives decreasing, consciousness converging toward unity. And when it reaches perfect unity, when there's only one perspective left, when observation can no longer differentiate itself, that singularity of consciousness, that final unified observation, transforms into infinite differentiation again. The one becomes the many. The end becomes the beginning. You are not witnessing the universe. You are the universe witnessing itself. Looking beyond the limit, so are you ready to look beyond the limit? To understand that everything you perceive, every star in the sky, every particle of matter, every moment of time, exists because you are observing it into being? To realize that the cosmic horizon isn't a boundary in space, but a boundary of consciousness? To accept that you've done this before and will do it again, an infinite number of times, bringing the cosmos into existence through the simple act of observation? The edge of the universe is the edge of your ability to create reality through consciousness. And consciousness, unlike matter and energy, doesn't obey the laws of physics. It creates them every time you observe, every time you measure, every time you become aware of anything. You're collapsing infinite possibility into singular actuality. You're bringing the universe into being. The nameless phenomenon at the cosmic horizon, it's not out there. It never was. It's in you. It always has been. It always will be. You are the observer at the edge of the universe. You are the consciousness that makes reality real. You are the eternal loop, playing out its cosmic drama an infinite number of times. And now you know.